Let's elaborate De-Bruijn graphs more with this example, which is we derived from the literature coming from Charles Dickens, and this is from his essay A Tale of Two Cities, written in 1859. So guys, the passage is something like this. So why we put it here? The example, obviously I'm quoting somebody in the end of these slides, so I've actually gathered from different literature. So where I found this example interesting, people are using this to elaborate on this De-Bruijn graphs. So here we have repetitions, so where we can have repeats also in this example. So it says, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness, it was the epoch of belief, it was the epoch of incredulity. So we take those fragments and we make their short reads, right? So these are our sentences. When we make those reads, they come out at random, something like this. So these words are these, fragments or reads, some of them, and they make no sense, but we need to put them together. We need to get that passage back from these reads. So we have tens of millions of reads, and the question is, how do we assemble them? So let's try this De-Bruijn approach. So we convert those reads into Kmers. Here we select our read size, or sorry, Kmer size as k is equal to 3. So we take read 1, so it can be broken down into like first we start with THE, next one is we start from HEA, we start from EAG, and so on. So in this way we can have those Kmers coming out from this read and from the rest of them. So in the end we have broken our reads into those Kmers. What we do next is we built a De-Bruijn graph, we put those Kmers together, and finally we observe different paths, or we observe different options. So one way is we can see we might have overlapping words or we might have different words, but this is how we put them together. So there is one path going like this, the other one going like this, and so on. So in the end we put all these, simplify this graph, and what we get from here is something like this. So we have, it was the consensus amongst them. So here at this position we have these three words together. Then in between we have different options. We can have option 1, it was the best of times. Since we have repeats, so obviously our repeats are right here. And then we can have different options. So we can use, for example, this guy can concatenate these all these folks together, right? This off can be coming from so many sources, kind of repeat words over here, this one and this one, right? And then we can, when we use different combinations, we can come up with different sentences. But what we get in the end, did we get our passage? Let's see. Oh, wartime, it was the foolishness, st wisdom. Does it look fine? I don't think so. Same will be you guys. So is it a good assembly, approximate, close, bad? You can look into that. Can we have the exact sentence? It's complicated. So in this example elaborates that doing the genome assembly, it's not an easy task. The way nature has created, the God has created us, it's really hard to get exactly to what the exact sequence was, but we can have close approximation. So for example, in this assembly where we were using k is equal to 3, we were having something like this. We can improve our assembly, maybe we can use k is equal to 20, and then we get something like this, maybe better one. So maybe we might improve it with the longer k sizes. But does longer k sizes is a solution? Yes, no? What do you think? Let's look into here. So we have some different bacterias. They tried different Kmers, and percentage of genome they got in unique Kmers is something like this. So when they increase from 0 to up till 20%, so they can capture most of the genome while increasing the Kmers. But then up till K30, so most of the genome is in unique Kmers. And if we increase up to 90 around Kmer size of 150, still still you cannot capture the whole genome. Still there is some genome that remains non-unique. So increasing Kmers might not be the most optimal solution. Can be approximate, but generally you can use some K values around 30. What is the issue with the longer Kmers? We will look into some slides down below. That longer Kmers, they pose some serious issues, so we cannot use them. So using an appropriate size Kmer and storing information stored in millions of reads is an important aspect of De-Bruijn graph algorithm. And this example tells us one more thing, that assembly is not an easy task.